Laplace transforms efficiently via Maple. My library contains at least 16 ODE texts suitable for a first course in the subject. All have units on the Laplace transform. Some with the material at the beginning, so it can be used as a tool in the course, and some near the end as an afterthought. Almost all ignore a technological implementation, so the working tool is by far by hands manipulations. So that means there's a considerable burden of algebraic virtuosity required of the student in such courses. Now, conceptually, the Laplace transform is simple. You change an ODE into an algebraic equation, you solve that algebraic equation, and return from the algebraic equation to the analytic domain. Implemented in, say, Maple, this paradigm is easy to comprehend. Implemented with just pencil and paper, it becomes a slugfest. This webinar summarizes the amount of material needed for a by-hands study of the Laplace transform. And by means of some examples, points out how much simpler and more efficient Maple makes the study, learning, and doing of the transform. Let's begin with some initializations. I'm going to make use of something in linear algebra. I need the intrans package to get at Laplace, the Laplace command. Some aliases, this symbol, this script L for Laplace, and this L inverse, this is an atomic variable. This is the coded version of this atomic variable. Capital Y for the Laplace transform of little y, delta for the Dirac function, H for Heaviside, and a couple of typesetting things so that y and its derivatives are printed nicely. So what is the Laplace transform? It's one of many integral transforms. So here's various notations for it. Laplace transform of a function f of t changes it to a function f, and I use s as the transform variable. It's an integral transform, 0 to infinity, f e to the minus st. Since it's an improper integral, you really go to a finite upper limit and push that upper limit to infinity. Changes a function f of t to a function f of s. So since this integral has to exist in order for the Laplace transform to exist, we have a criteria. We say f is integrable, sufficiently smooth if you're talking about a Riemann integral, and of exponential order, that is, it's bounded by a multiple of an exponential. And as a consequence of this condition, a Laplace transform goes to 0 as s goes to infinity. So this is the mark of a valid transform. It goes to 0 as s goes to infinity. So what's the reason for Laplace transforms? Why do people use them? Well, in a differential equations course, you see a diagram like this in almost every text that treats it. You have an initial value problem for a function y of t. You take the Laplace transform of this initial value problem, it becomes what gives rise to an algebraic equation in the transform. You solve algebraically, and you end up with the transform equals. You then have to invert that, bring that back to the time domain, because initial value problem t is most likely time. Then you bring that back. So this is the solution process. Transform, solve, invert. Now, at this point in the course, probably some Laplace transforms are introduced. Now I'm going to use Maple to generate these Laplace transforms. If you have a constant, transform is 1 over s. Now this is the syntax in Maple. What are you transforming? What is the existing variable? What is the transform variable? T goes to 1 over s squared. T squared is 2 over s cubed. T cubed, 6 over s to the 4th. And you generalize and you realize t to the n becomes n factorial over s to the n plus 1. Now, at the same time, you want to look at inverses. So if you are inverting, going backwards from 1 over s, you would use the syntax. And here I've reminding you that this is an atomic variable constructed as we showed at the beginning. 1 over s becomes 1, 1 over s squared becomes t, 2 over s cubed becomes t squared, and so forth. Now, if you were to do this via an integral, and you wrote 0 to infinity, Maple would respond by saying, you need to be taking a limit here. So you can assume that s is positive, and then Maple will tell you what that integral is. And here we are showing that if you take n factorial over s to the n plus 1, you can invert that if you assume that n is a positive integer. Then you're going to get n factorial over the gamma function. But the gamma of n plus 1 is n factorial, so these actually cancel and you get t to the n. If you were to put n factorial over s to the n plus 1 and you hit it with a simplify while you were inverting, and simply assume that n is a positive integer, you get your t to the n. And then you take a few other functions like sine omega t. It turns out to be omega over s squared plus omega squared. And if you do it by integration, you can see here that it's an infinite integral, improper integral. You got to really be taking a limit. If you make an assumption on s, then you still have to simplify these radicals. And if you hit that integral with a simplify, assuming s greater than 0, you get omega over omega squared plus s squared. If you're going backwards, directly sine omega t. Cosine behaves the same way, except that its transform is s over omega squared plus s squared. E to the at transforms to 1 over s minus a. Here is its inverse. Hyperbolic sine and hyperbolic cosine, which you could construct from the knowledge of what the transform of e to the at is. Hyperbolic sine is a over s squared minus a squared. S squared plus omega squared, s squared minus omega squared, or a squared. S over s squared minus a squared, s over s squared plus omega squared. And the inverses behave the way you would expect them to. Now, of course, these examples could be pulled out of a table. They can be constructed by hand at a great deal of labor. A student would need to know his or her calculus, right, based on calculus. Or they could use a tool like Maple, as we've seen. Embedded in this material, we have the operational laws, the things that make integral transforms workable. Here is the transform of a derivative. Now I've shown the transform of a first, second, and third derivative so that the pattern could become visible. For a first derivative, you multiply the transform of y by s. But then there's always a detail. So you got to subtract y at 0. If you go up the scale, you'll see s cubed, s squared, s to the first power, s to the 0 power. Then you see functions, no derivative, one derivative, two derivatives. So s's go down, derivatives go up. There's mastery of the derivative law. If you multiply by t and take that transform, it is equivalent to transforming just y and taking the derivative with respect to s. Now notice there's a parallelism here. If you take the transform of a derivative, you multiply by s. If you multiply by t, you differentiate the transform. There is a detail. There's a minus sign. If you transform an integral of y, you divide by s. But if you divide by t, you integrate the transform. And in each case, there's a detail. You're integrating 0 to t for the detail here. And here the integral is from s to infinity. There's a detail to remember there. So these are called the operational laws. And a way to get them across is to teach differentiate and multiply or multiply, differentiate. Integrate, divide, divide, integrate. So you speak of the time domain and the transform domain and you spell it out. Transform a derivative, you multiply the transform by s, multiply the function by t, you differentiate the transform. Transform an integral, divide by s, divide by t, integrate the transform. And this is just spelling out, again, what these operational laws are about. So if you're going to work with a pencil and paper, you've got to know these transform laws, these operational laws, because otherwise, how do you get a transform of something like t times e to the 2t? Now, in addition to these operational laws, there are the shifting laws. Some books say first and second, some books say first, second, and third. What's the first shifting law? If you multiply by an exponential, you shift in the transform domain. The second shifting law says if you shift in the time domain, you multiply by an exponential in the transform domain. In other words, you get the transform of f of t. That's f of s, big F of s. And you multiply that by e to the minus as. And there's a detail. You have to have this function, this shifted function, multiplied by a Heaviside function. And it's also shifted with the same amount, t minus a. This is a very difficult problem. Some functions make it easy to arrange shifting. Sines and cosines and exponentials and polynomials, they are easy to write in the form t minus a by taking f of t, writing t minus a plus a. Well, sine of t minus a plus a splits, right? You got a trig formula for that. A student has to be algebraically versatile in order to be able to see that happening here. So there is, in some books, a third shifting law, which is really a variant of the second one. Suppose you have a function g of t multiplied by a Heaviside. Well, rather than mess around with this t minus a plus a business, it turns out you can still multiply by e to the minus as, but you shift g and take the transform of that shift. So, two shifting laws or three shifting laws. Algebraic burden is large. And if you're working with a pencil and paper, you will spend time and you will be basically teaching the student algebra and trigonometry, not the use of the Laplace transform. There is another law, rule, result that's useful, and that's a recipe for the transform of a periodic function. Suppose f is a periodic function with period p. Well, the transform is integral 0 to infinity. But if you integrate over one period and you look at the sum of the integrals of successive periods, you realize it's a series. And this factor out front is the sum of that series, geometric series. So this turns out to be a useful formula. Probably toss that out at students. And you add it to the computational burden that the by-hand student, pencil and paper student, has to become facile with. And then we come to the convolution of two functions, f of t, g of t. Their convolution, I use a star here like most books use. The convolution of these two functions is a new function of t, and it's defined by either of these two integrals, which are equivalent. Shift in t, g, shift in f, g, shift in g, leave f alone. I would tell my students this is f of t minus a dummy variable, t minus dummy, g of dummy, f of the dummy, g of t minus the dummy, and the integrals are 0 to t. So this defines a convolution of f and g. It's useful in the applications. That is what it is. And it involves calculus if you're working by hand. And if you teach the convolution product, you absolutely have to mention the convolution theorem. And what does the convolution theorem say? The transform of a convolution is the product of the transforms of the two individual factors. And what good is that? Take the inverse on both sides. So I've switched these two sides. If you invert this Laplace transform, you end up with the convolution sitting here. And so this is a recipe for finding the convolution. You get the transforms of the individual factors, multiply those functions together, and invert that product. And you're looking at the convolution of f and g. Useful theorem. I remember some of my engineering colleagues at Rose-Hulman obtaining a convolution by some hand-waving stuff that just broke my heart when you have a tool like this available to make it so direct. Now there's one more chunk that must be included in this body of information that makes the Laplace transform useful and workable, and that's the Dirac Delta function, the impulse function. And I would approach this with my students by a question and answer. And the question is, which function f of t has as its transform 1? Now remember what we said earlier. A good Laplace transform goes to 0 as s goes to infinity. This will not go to 0 as s goes to infinity. So there's that question that sits in front of the student. What function f of t has as its Laplace transform 1? Well, what's the answer to this question? The answer is there is no function f of t, no pointwise function f of t that has its transform 1. So what do? We invent something. Now, you and I know that this invented thing is a singular distribution. But we can't tell that to our students. They don't know what that means. So we invent this thing, the delta function, and we say its transform is 1. It's not a contradiction because this is not a pointwise function. It's not even a function. It's a functional. Now, I did not like to sneak up on this thing via a limit of piecewise things because it requires an interchange of limit and integral that's just not valid. If it were valid, then you wouldn't have had to invent distributions. So I avoided that approach. It gives some intuition. It's up to the individual instructor how they want to handle it. But it is a very useful object to have in the domain of Laplace transforms. In fact, any transform, any integral transforms. How you get it across to the students, I'll leave that to you. And now I'd like to look at some examples using Maple compared to pencil and paper. And I asked myself the question, why students are required to learn this by hand stuff and not be allowed to use technology. And I believe the answer is the test. As you test students with a pencil and paper, and so they have to learn this pencil and paper stuff. But if they have to master this pencil and paper stuff in order to take the test, then they look at the explorations in Maple as added work, and they say, why am I doing this computer stuff when I have to master the pencil and paper stuff in order to take the test? And I don't have an answer to that. But anyways, let's look at a couple of examples here. Here's a Laplace transform that we need we give to the students to practice on. T, so you're multiplying by t. E to the 2t, you're multiplying by an exponential. Basic function, sine 3t. If you let Maple take the Laplace transform, the answer is immediate. Bing. There it is. How do you do this with a pencil and paper? Well, it depends on which law you apply first. Here's one way to do it. Think of the shifting law multiplied by e to the 2t. And what are you multiplying by e to the 2t? T sine 3t. So you take the transform of t sine 3t, and then you shift s to s minus 2. But how do you take the transform of a product by t? Well, it's the negative derivative with respect to s. So you begin with the transform of sine 3t. You take its derivative, put a minus sign. All right. There's the transform of sine 3t. You take the derivative, the minus sign. You now take this and shift s to s minus 2. You have the transform that you would have gotten here by Maple much more easily. So this is the kind of virtuosity down here in this big box. That's the kind of virtuosity that we expect our students to have at their fingertips, but they end up learning algebra and calculus instead of seeing the Laplace transform for what it is. Anyways, that's my rant. This is why I say it is so much more efficient. Just simply say, we're going to use Maple to do the stuff that would otherwise have to be done by these tedious by hands methods. So here's a second example. Take the transform of the function sine t multiplied by the difference of these two Heaviside functions, and the difference of these two Heaviside functions is what I call a pulse. 0 until you get to 3, jumps up to 1, stays at 1 till you hit 5, drops back to 0, and it's off. So it's like turning a switch on at time 3 and turning it off again at time 5. This is what that function looks like. So I've just plotted h of t. So 0 until you get to 3, 0 after 5, between 3 and 5, you get sine t. This is the piece of sine t that lives between 3 and 5. If all you've got is the second shifting law, then you have to write sine t as something as a function of t minus 3. Now, for sine t, you can do t minus 3 plus 3 and use the trig formula to split this. But now you've got a h of t minus 5, so you have to have sine t minus 5 plus 5. And you have to use this sum law, trig law, twice. And so you now have this and this. Well, now you can apply the second shifting law, and you get this times the transform of sine t, and all of this times the transform of cosine t, where these exponentials arise from the second shifting law. And so your final result is this. Alternatively, you take the Laplace transform of what you're given, and you get this. So, what is the advantage of requiring this virtuosity in algebraic manipulations as opposed to saying, look, we just need the transform of this function. How do we get it? So, I will get off my soapbox. I just don't understand why we torment our students with this kind of stuff. A third example. This one, differential equation, initial value problem. This is a damped oscillator, and it's being poked at t equals 2. And you model that with this Dirac Delta function. And the strength of the poke is 4. So if you're doing it with Maple, you just say, give me the Laplace transform of this equation. You get this. You solve it for y. There's your y, there's your y. You get this. You insert the initial values. Y at 0 is 1, y prime at 0 is equals 2. You now have to invert this. Well, hit it with the inverse Laplace transform, and there's the solution to this problem. And if you draw a graph, you will see you start out, it's a damped oscillator, but because of the initial conditions, it starts to go up, and then it starts to decline. At t equals 2, you poke it, you give it a positive jolt, climbs to here, and then it decreases, diminishes because it's a damped oscillator. So I assume that if you're looking at this initial value problem, what you really want to know is A, the analytic behavior, and B, maybe the graphical behavior. If you only have pencil and paper, you might get this. How are you going to get this graph with a pencil and paper? It's not going to be easy. But working with a pencil and paper, look at the algebra that you're asking the student to be facile with. You've got to invert this transform. So here it is, right here. You have to split that into two fractions. This one with no exponential flag, I call it the shifting flag. This exponential tells you you're going to need the shifting law. To get this transform, complete the square in the denominator. That's one way to do it. Complete the square in the denominator, and you see s plus 2. So this s plus 6 in the numerator has to be written as an s plus 2. Well, 2 and 4 is 6. So you have a second fraction. The denominator here, complete the square, s plus 2. But this s also has to be an s plus 2. So you add and subtract a 2, and this minus 2 out front, you get a 4. So s plus 2, s plus 2. This is a minus sign, hyperbolic cosine, shifted because you take care of the shift with exponential. This hyperbolic sine is a 4, and then e to the minus 2t because it is s plus 2. So now here everything is s plus 2. This is the shifting flag. It tells you that you're going to need a Heaviside function. So this is 4 e to the 4. So you have the shift here, e to the 2t plus 4, hyperbolic sine, Heaviside. So in order to get this information analytically and graphically, we are asking the students to go through all of this algebra. It doesn't make sense to me. But anyways, I am on the soapbox, and I can say what my opinion is. I leave it to you to decide what you want to do to your students. Example 4. We have a system of linear first order constant coefficient equations. It's phrased as an initial value problem. And we're going to solve it with the Laplace transform. So that's a tool that you can use to tackle these systems of equations, which is the staple of differential equations course. So you take the Laplace transform of this equation and this equation, you get these two equations. X is the transform of little x, y is the transform of little y. Write it as a system in x and y. So this is the matrix that multiplies the unknowns x and y, and these have to equal these initial values, 2 and minus 1. So you solve this system. Well, now you've got to have a way of solving that system. Turns out that x is this and y is this, and now you have to invert. So a very simple idea. Take the Laplace transform of the system, solve for the unknowns, the unknown transforms, and invert. Bogs down in a bunch of linear algebra. I would prefer that that linear algebra be turned over to Maple so that the essential concept is not lost. Well, in addition to my harangue about the use of Maple to do a linear system, there's another thing that you can do with this Laplace transform here on the linear system. Let little v, bold, be the vector of functions x of t, y of t, and big V be their transforms. Now look at the transform of the system v dot equals av, with the initial values being some initial vector v0. If you take the transform, you get sv minus v0, where this is the vector s times the first component, s times the second component, and that equals AV. So solve for V. It's the inverse of SI, where that's the identity matrix, minus A times V0. This is just algebra. This matrix, phi, that's this guy. Turns out that's the fundamental matrix. But you can get that fundamental matrix through the Laplace transform. Here it is the inverse. Well, clearly you want to do that in Maple, SI minus A inverse. You don't want to be doing that by hand. Take the Laplace inverse, multiply the initial vector. That's equivalent to the statement, the fundamental matrix times the initial vector gives you the solution. So here you have a recipe for the fundamental matrix. The inverse of SI minus A inverse. And here it is done in Maple. What would you do to do that in Maple? Well, you need the matrix A. And here I'm just using the matrix exponential command. That's why I loaded the linear algebra package. Matrix exponential. Here's the matrix exponential. Well, let's use this recipe. SI, and this is how you get I. You need to say identity matrix, two-dimensional, minus A inverse, and you're taking the Laplace transform, and I'm mapping that transform across the two components of this inverse, and I get this. And if I multiply phi times the initial vector, I get this solution. So another use of Maple in dealing with systems, linear systems. Now a fifth and final example, convolution. I'm going to restart and then bring back some of the tools that I need in plotting tools and these aliases. So just to have a clean slate. Let's compute a convolution product. Convolution of sine t and cosine t is defined by an integral, 0 to t, and I've picked the form where I shift, I'll put the dummy, t minus dummy in the first factor. This integral can be done in Maple. It can also be done by hand and using calculus. Here's the answer. T over 2 sine t. So here's a convolution that can easily be done either with Maple or without Maple. Here's a more difficult convolution to obtain. we'll use this integral. T minus dummy, g of dummy. Here is the function f. Here's the function g. They're both piecewise. This is the integrand. What does that look like? I mean, think about it for a second. The only time this integrand is non-zero is when these two terms multiply each other. And so what conditions indicate or guarantee that you are looking at this times this? Well, here are the inequalities that determine when this integrand is non-zero. And if you want a picture of it, you can do a 3D plot of this integrand. And it appears to be non-zero over a parallelogram. And if you do a graph of these inequalities, you see that you have this parallelogram here. In green, that's where this integrand is non-zero. In the red is where it is 0. And so you look at this graph and you realize the integrals are in integrals of in x, right? Here we're using dx. So you're integrating x from 0 till you hit this line here. This is the line t equals x or x equals t. So 0 to t, and then you have these two factors multiplying each other. In this region, x goes from this line, which is t equals 1 plus x, to this line, which is t equals x. So t from t minus 1 to t is product. And you go as far as x equals pi, that's pi right there. And in this region, you're going from t equals 1 plus x to pi, so x equals t minus 1 to pi. You get this integral. You evaluate these three integrals, and here it's 0 because it's up here, 0. You get this stuff. Quick simplify gives you this expression. So this piecewise function is the convolution of these two functions. I don't think that's an easy one to get in pencil and paper technology. I think that's very difficult. There is a much easier way to get this convolution, and it's by the use of the convolution theorem. Remember what the convolution theorem says. The Laplace transform of a convolution is the product of the transforms of the factors. And if you invert that, you get the convolution is the inverse of the product of the transforms. And if we do that here, this is the transform of f. This is the transform of g. Multiply f times g. Invert that. And if you do a little bit of cleaning up, this expression matches this expression. Except for, well, no, the 2 is in the same place. And if you want to draw a graph, you can see what the convolution looks like. So I believe the way to get through this material conceptually and computationally is with a tool like Maple. The restriction to pencil and paper, in my mind, is the exam is the tail wagging the dog, and I wish there were a solution to that problem. So if you want to copy this worksheet, here's my email address. Contact me. Ask me what you need, and I'll have your email address that I can send you back a copy of the worksheet.